Hi everyone, welcome to Om Learning Lab. In this video, we are going to solve the problem find median from data stream. Now this is one of those problems which is listed in LeetCode's top interview 150 set of problems. This is quite a famous problem asked in interviews, so let's just get into it. The problem statement itself is fairly simple, which is that they have defined what the median is for an ordered integer list. So by ordered integer list, they mean that you arrange all the numbers in a list in ascending order, and the median is a middle value. So if the size is even, there is no middle value, so you take the average of the middle values. For example, if there are 3 elements, median is 3, which is the midmost element. If there are 2 elements, so the number of elements is even, there is no exact middle element, so you just take the average of the two numbers. That's it. Now, in this problem, what happens is continuously one after other numbers will keep getting added, keep getting sent to us, and at any point of time, they can ask us to tell the median. So that's the challenge in the problem. So there is this median finder class that they have defined here, and median finder will initialize the object. Add now function adds the integer to the data structure, whatever data structure we are going to come up with for optimal solution, that is. And find median will finally return the median of the elements we have encountered so far. So that's the problem. And here they have defined how they initialize the structure. So this is the standard OOPS concept, that you initialize an object of the median finder class and then you use that object to call the respective functions. So they have given some examples over here, but I would preferably take my own example, because as you can see that in this example, the numbers kind of come in ascending order. So, I mean, that's kind of not really a good case, I would say. A better case would be to have a jumble of numbers so that it's easy to understand what could be the edge cases of the problem that we are supposed to handle. So let me go to the notebook and try to take some random test case. So for example, let's say the first number that we have is 4. So let me make two tables. In fact, let's say let me take two tables. Here is the number stream. Okay. This is the stream of numbers. And let's say this is the median so far. Median. Now, let's say the first number was 4, so the median will be 4 because there is just one number. Let's say the second number is 1. So the total number of numbers for now is just 2. So it's 4 plus 1 by 2, because since there are even number of numbers, there is no exact middle element. So it's 5 by 2 or 2.5 is the median. Let's say the next number is 2. Now here is where it gets interesting, that we need to use some sort of data structure or some sort of algorithm which will be able to capture that when you have 3 such numbers, the median will come out to be 2. Similarly, let's say the next number is 3. If we arrange them in sorted order, what will it look like? It will look like 1, 2, 3, and 4. So you should be able to capture that these two are the midmost elements. So the mean will be 2 plus 3 by 2. Or 2.5. So these are some of the nuances of the problem, that regardless of how your data stream looks like, you need to be able to find exactly what the median is. Now, the brute force approach, or the first approach that would come to mind is, you just maintain an array, for example, and keep on adding the elements that you see. And the moment they ask you to find the median, we'll just sort that array and pick the midmost element and keep repeating the process. So what I'm saying is, let's say I defined some array here, which was empty. So I saw 4, I inserted 4. Then I saw 1, I inserted 1. When they ask me to find the median for 1 and 4, I will call a sort function that will make my array 1, 4. And then the median is, in this case, median won't get affected since there are two numbers. But as we will see next, that sorting kind of becomes important. So here the median will be 2.5. Then you have 2, so array becomes 1, 4, 2. Then if you are supposed to find median for this, you have to again sort this. So 1, 2, 4, and the median is 2, so on and so forth. It's easy to see that if we follow this approach, although this is the brute force approach, which is easy to come up with, this is not really efficient. It's not efficient because you're calling the sorting function repeatedly. We know that sorting function takes n log n time, so the time complexity is n log n. That is the most efficient sorting algorithm that we have, merge sort. It will take n log n time. And if we keep on calling sorting function each time we have to find a median, worst case there can be n calls. So asymptotically speaking, it will be something like n square log n, which is not really efficient. I mean, we already have a quadratic term multiplied with a logarithmic term. That's just not a good time complexity to work with. So we'll have to find an efficient approach or a smart approach, so to speak. Now, in order to come up with the smart approach, we need to go back to the basics of the problem. What is the median? So a median is basically a number which lies between two sets, a set which is less than or equal to the number, and a set which is greater than or equal to the given number. So what I'm saying is, let's say for a given stream of numbers, let's say x was the median. Then that means that on its left hand side there will be a set. Let's say this set contains all the numbers which are less than or equal to x, and on its right there will be another set which will contain numbers which are greater than or equal to x. I mean, that's just generally speaking, right? So it lies in the median. That just means that it has a left side set and a right side set, and both these sets have to have same number of elements. Assuming that currently we have odd number of elements, and if this is the odd median, if we have the exact median available, in that case this should be same. Like, let's say there are a elements in this set, here also there should be a number of elements, and the total number of elements so far is 2a plus 1, right? That's basically what should happen. Or what could happen is, let's say there is no such x, I mean there are even number of elements, in which case you pick the largest element from the left hand side and you pick the smallest element from the right hand side. So you take max from the left hand side and you pick min from the right hand side and you take their average. That is your median, right? We will understand this concept using this particular example itself, which I walked over in the beginning of the video. So in this case, what happens? So when 2 was our median, basically the sets look something like this. 2 is in the middle. In the left hand side set, there is just 1. In the right hand side set, there is just 4. But the moment 3 came into the picture, what will happen is 2 should ideally go to this particular set. 3 should come to this set. So our sets will be like 1, 2 on the left, 3, 4 on the right. When someone asks us to find the median, pick the largest element from the left hand set, which is the lesser element set or the smaller element set. Pick that. Pick the smallest element. Pick the smallest element from the set which contains the larger set of elements, which is 3, and take their mean. So 2 and 3, their mean is 2.5. Now, this approach could be helpful if you are able to come up with some data structure which is efficient at giving max and min. I mean, basically that's what we are doing, right? So for every element that we see, we'll have to insert it into one of those sets, either the set which contains the smaller set of elements, or the other set which has the larger elements. And when we are asked to find the median, if the number of elements is odd, then you just pick the middlemost element. We'll have to handle it a little better. I mean, one of those sets in practical implementation will have one more element than the other in case of odd number of elements. So ideally speaking, when we have 3 elements, 4, 1 and 2, when we actually implement it through any data structure, one of these will have one more element, right? And if it's even, then we just pick the largest element from the smaller set and the smallest element from the largest set and take the mean, as I explained. Now, which data structure comes into mind which can efficiently give us the largest element or the smallest element and efficiently manages them as well? The most efficient data structure present to us are the heaps. Because in heaps, any kind of insertion that you do is logarithmic. There is basically a shift operation that happens in heaps, which ensures that whatever element you want to insert into a heap takes logarithmic time. It's basically an implementation of a binary tree. So that's what ensures that all the labels, they're add up in log base 2. So ultimately, the time that is taken for any insertion or any deletion is logarithmic. And the best part is, any kind of operation where we have to find the max element or find the min element is basically picking the topmost element of the heap. So for a max heap, the maximum element will be the topmost element or the root node of that particular heap. And in a min heap, the minimum element will be the root node of that particular heap, which can be just found out by top function, or it depends on the kind of language you're using. But the time complexity will be big of 1, which is constant, which is the best possible time complexity we can get. So we can use Max-Heap and Min-Heap as data structures for this problem. Let me switch to another color. So we'll be using Max-Heap and Min-Heap for these problems. So Max-Heap will be on the left-hand side. So this will be my Max-Heap, because remember, on the left-hand side, we have the smaller set of elements and we pick the max from those. So we need a Max-Heap because we need to find the largest element. And on the right, we'll have a Min-Heap. Okay. Now, we know how to process these elements, but the key part is how to handle when the total number of elements is odd. I mean, when total number of elements is even, we'll just pick the largest and the smallest from the two heaps and take the average. But when it's odd, like I said, in practical implementation, one of these heaps will have one more element. So there is a balancing of the heaps which is required. So here is what we can do. We will choose one of these heaps to be the default heap for any kind of insertion. So let's say that heap is max heap. Let's just assume that in my implementation, I'm saying that max heap will by default be that heap which will take any element that is coming up. So in my example, the elements were 4, 1, 2, 3. So let's just take that example only. So we have 4, 1, 2, 3. Let's say we have 5 as well. So when 4 comes into the picture, like I said, by default, I'll be inserting that in the max heap. So there is nothing in the max heap. Initially, both these heaps are empty. These are empty. So this is empty. So just push into the max heap. So 4 comes into the max heap. Then 1 comes into the picture. Now max heap is not empty. There is some element in the max heap. So what I can do is, if max heap is empty, we push the element into the max heap, or whatever element we are seeing, that element has to be less than or equal to the largest element in the max heap. Because please think about it, the largest element in the max heap is basically the largest element in the smaller set by definition. That is how we have approached the problem. So whatever element we are seeing, if we want to insert it into the max heap, it has to be less than or equal to the largest element in the max heap. So either the max heap is empty, in which case you insert the element into it, or the given element has to be less than or equal to the topmost element in the max heap. So 1 is less than or equal to 4. Yes. So we insert 1 here as well. But here we will have to do a balancing of the heaps. Why? Because see, if we need the two sets to be as equal as possible. Remember, if there are even number of elements, both these two sets need to have exactly same number of elements, so that we can find the largest from left, the smallest from right, and take the mean. Or if the total number of elements is odd, we also need them to be balanced. Like one set can have one more element than the other, so that we can pick that particular element. For example, if we have 1, 4, and 2, our max heap can have 1, 2. Our min heap can have just 4. And we know that since this particular set has one more element, this 2 is my answer. Right? Because this is the smaller set, largest element from the smaller set, and this has one more element. So that has to be the median. So there is a balancing required. So at this point, since this has 2 elements, this has 0, we'll see that, okay, it's not balanced because it has 2 more elements than the min heap. So what we do is we'll send the maximum element from the max heap to the min heap. So this goes away and comes here. And it is not a problem because effectively what we are doing is we are sending the largest element from the max heap to the min heap. So that ordering that on the left side we have the smaller elements, on the right side we have the larger elements, still remains intact. Right? That is important to note that when we are doing this balancing, we are not in any way contradicting our problem solving or our approach, because effectively still smaller elements are on left and the larger elements are on right. So after balancing, we have 1 on the left, 4 on the right. Again, I am repeating, we are balancing because we want the two sets to be as close as possible. Here 4 and 1 were in the max heap, there was nothing in the min heap. So there are 2 elements and there are no elements. That is the unbalanced state. Then we have 2. So we'll do the same comparison. Is 2 like less than or equal to 1? It's not. So then insert 2 into the min heap. And as a rule of thumb, we'll have to ensure that one of these sets has larger elements. I mean, it's a good practice to do that. We just want to make sure that, we know which set will have one more element in case of the total number of elements being odd. So again, we'll do a check that here min heap is having one more element than max heap. So let's not insert 2 here. We'll take 2 to this position. I mean, min heap will return the minimum element anyways, right? So again, that ordering remains preserved. Smaller elements on left, larger elements on right. And since there are odd number of elements, we have 1 and 2 elements in max heap and just 1 element in the min heap. And we have arrived at this particular condition, if you observe. So if anyone asks us what's the median, we know that max heap has 2 elements. Min heap has just 1 element. So the largest element of the max heap has to be our answer. Next, we have 3. Is 3 less than or equal to 2? I mean, the largest element from max heap? No. So it has to be pushed into the min heap. If someone asks median now, take the largest element from the max heap, take the smallest element from the min heap, take their mean, that's your median. One final example, let's say we have 5. Is 5 less than or equal to 2? No. It has to be inserted into min heap. Alright. But min heap has larger elements than max heap. We want to enforce the rule that max heap has one more element, just so that we are sure that max heap, the left hand set, is the set which has more elements in case of odd number of elements. So 3 will be removed. Since it's the minimum element, it will come to the max heap and the median will then be 3. We know that max heap has one more element, so the maximum element has to be the median. So that's how we can implement this, and this implementation will be really efficient because we have n elements in total and all we are doing is we are inserting into one of those heaps, max heaps or min heaps. So asymptotically speaking, in worst case, the time complexity will be big of n log n, which is much more better than the brute force complexity, which was quadratic multiplied with logarithmic complexity. So this is L log n time complexity. And space complexity is basically we have 2 heaps, and at any point, if you add the total storage space of the heaps, they can at worst store big n elements, right? So if left hand side has x elements, right hand side has y elements, total space taken is x plus y, and x plus y will always be less than or equal to n, assuming n is the total number of elements that we have. So big O of n is the space complexity, big O of n log n is the time complexity, again because worst case we have n number of insertions into the 2 heaps and each kind of insertion takes log n time. So that's why I'm taking the multiplication. So this is the time complexity and this is the space complexity, and this is the whole approach. We can go ahead and implement. Just as a reminder, what we are doing is we want to maintain a left hand set and a right hand set. Left hand set returns the maximum element, right hand set returns the minimum element. So that's why in order to implement that idea, we chose those data structures which are really good at doing that, which are heaps. So take a max heap on left, take a min heap on right, and then do the processing which balances the heaps. And as a rule of thumb, I am trying to maintain the left hand side heap to be the one which has more element in case of odd number of elements being in total. So that's what we are doing. In case any heap has more number of elements than the other, or in other case, in other words, that is unbalanced, then we'll balance them. We'll put if else conditions in place, if condition checks in place, and we'll balance those heaps. And the ordering will remain preserved because maximum element from heap will go to the min heap, and the same ordering that smaller elements on left and larger elements on right will remain preserved. Similarly, if minimum element from min heap goes to the left hand side, again smaller elements are on left, larger elements are on right. So the ordering remains preserved. This will become more clear as I go ahead and implement the code. I will be implementing the code in C++. So let me go ahead and implement it. Okay, so this is the problem statement, and let me just start writing the code here. So I'll define in C++, we have priority queue data structure. So priority queue, we have integers. This is just how we implement it. So when you write something like this, this is your min heap. That is, this is the definition of a min heap in C++ STL. And max heap is just standard. So priority queue and max heap. That's it. So we have our min heap and max heaps defined, and we know that this median factor function is basically to initialize the object, but here we are just defining or defining the objects in public space, and we don't need to initialize them to specific. So by initialization, I mean that in some problems, whatever variables that we have defined, we need to assign some initial values to it. But here there is no need to do that. So we can just leave this function as it is. We don't have to do any modifications because there is no need to initialize. We have defined those variables in the public section itself. So they are accessible to all the functions. We don't explicitly have to initialize them with any values. We can directly come to the add num function. So here we'll implement the idea that by default, we have to insert everything into max heap. By default, insert into max heap. So how we do that is if max heap dot empty, let's say there is nothing present in the max heap, or if the largest element in the max heap is more than num, or like the element that we are seeing, it is less than or equal to max heap dot top, the largest element in the left set, only then it should be inserted into the left set, right? Because an element is going to the left hand set means that it is small in nature. How to check that is by this condition. The largest element in the max heap, that should be greater than or equal to the given element. So in that case, we just push it into the max heap dot push num. Else, what we can do is we can push it into the min heap dot push num. But we have to implement balancing idea here. So we'll have to balance the heaps. So for balancing, we can check that if, let's say, at any point of time, max heap dot size is equal to min heap dot size plus 2. Remember that I am not putting a greater than or equal to sign here because, the moment it becomes equal to min heap dot size plus 2, I am balancing. So at no point of time it is going to be more than that. So I'll just ensure that. What I can do is if max heap has larger elements, then just push the largest element from the max heap into the min heap. So that is min heap dot push max heap dot top and max heap dot pop. So that's what we are doing in the example as well, right? So if max heap has more elements, for example, it had 1 and 4 and min heap was empty, largest element from the max heap, which is 4, will be pushed into the min heap. So min heap would have 4 and max heap would have 1. And the ordering still remains preserved. That is smaller on the left, larger on the right. So that is the balancing that we need to do, and we need to, like, just for convenience, I want to enforce the idea that if at all there are odd number of elements present, then I want my max heap to be the one which has the larger element, which has more elements. That is, it would have one more element than the min heap. So enforce the max heap to have more elements, max heap to have more elements. How do you do that? So let's say in case if min heap dot size is max heap dot size plus 1. So either they both have same size or max heap will have the additional element. That's what I want to enforce. If this happens, then max heap dot push. So max heap will have the smallest element from the min heap, which is min heap dot top, and we remove min heap element, min heap dot top, the smallest element from the min heap. So that's it. That should be enough for the implementation on how to insert elements. By default, we insert into the max heap if it's empty or the element is smaller than the largest element in the max heap. Otherwise, we push into the min heap, and we balance the two heaps. That is, max heap cannot have two or more than two elements than the min heap. So difference can be at most 1. And if at all there are odd number of elements, I want the max heap to have the lead. Now, implementing find median is a piece of cake. The total number of elements would be max heap dot size plus min heap dot size. If total is odd, so this is just checking if the total number of elements is odd, then we can just do return max heap dot top. So this is where the convenience comes in, because I know that if the total number of elements is odd, I have ensured that the larger number of elements are in the max heap, and the largest element in the max heap is my answer. So if I hadn't implemented that, I would have to add some additional conditions, that which one of them has odd number of elements, return that, so on and so forth. Else, we can do return. So by else, I mean that the total number of elements is even. So you pick the largest element from the max heap. So max heap dot top, and the smallest element from the min heap, which is min heap dot top, and you take that average. Return max heap dot top, min heap dot top, divide by 2. That's it. And I'll just add a return 0 here, because functions cannot be returning nothing. So this will never be called, because effectively if else condition is there, so either one of these conditions will be met, and I think I have to typecast into a tuple. Let's run this. This should work. There is a issue. What's the issue? Mum. Where have I written mom? So it's no. Just a typo. Should be fine. Compilation error. Mix it. This is max. Okay. Let's try to sum it. Yeah, it got accepted, and so that was the solution. Just going back to the code, that we are implementing min heap and max heaps insertion and balancing, and enforcing the idea that max heap will have the lead in case there are odd number of elements. And one more thing which is important is that we actually kind of have to do this. Like, we have to enforce that max heap is the one which has more elements than the min heap in case of odd number of elements, because if we don't do this, if min heap has more elements, then there could be a case that min-heap has 2 or more elements than the max-heap. And here we are only doing the check for max-heap having more elements than min-heap. So if we don't implement this part, basically, we'll have to do one more check here that, max-heap could have 2 or more elements than the min-heap, or min-heap could also have 2 or more elements than the max-heap. So that would be like double balancing the heaps. That would be much more hectic to handle. So that's why I have just ensured that max-heap will be the heap which will have more elements. So by ensuring that, I just need to implement only this if condition, that in worst case, max-heap will have more elements. If that happens, just do this balancing. Otherwise, I'll have to do more checks conditions as well. So that was the reason for implementing this for people who are wondering. And the rest of the part is fairly simple, directly taken from the notes. It's the direct implementation of these ideas. Once again repeating, this is the time complexity, then this is the space complexity, which are really efficient in nature. Quite a handy problem, quite a famous problem in coding interviews. I hope you learned something. I hope you at least got the intuition of the solution, how to approach the solution, how to come up with the data structures, and then finally, how to implement them efficiently to get the solution done. That's all for this video. See you in the next one. Bye.